The quest for Mars. An odyssey like no other. 6 lives depend on the most advanced engineering ever imagined.
KC safety mission assurance. KSC SMA is go.
2.5 years and hundreds of millions of kilometers across the last and most hostile frontier.
Range weather.
There's no forgiveness in space. You get it wrong, you kill people, raid explorers, and sometimes they don't give you a second chance.
Standing by for retraction of the crew access arm.
Main engine is now in start position. T-minus 10 seconds, go for main engine start. We have main engine start. 3, 2, 1, and liftoff, liftoff. Mankind's first journey to Mars is on the way.
The vehicle has cleared the tower.
It may sound like science fiction, but it's not fantasy. A multi-nation expedition is going to Mars. It could happen in our lifetime.
We are practically ready to start the production of the ships for the Martian expedition.
Mars is at least 1,500 times farther than the Moon. It will take more than 2 years to make the round trip. A perilous voyage into deep space, past a threshold we have never crossed. The point of no return.
Mars 1, you are go for the trans-Mars injection. Roger, we are go for the TMI burn.
We're talking about a dangerous undertaking that really is going to require a lot of skill and a lot of effort to get back safely.
Their reliance on their hardware will go to an order of magnitude beyond anything that's been done previously.
To make the voyage, we'll need to design a whole new fleet of spacecraft, starting with bigger, more powerful launcher vehicles. They must lift hundreds of tons of equipment and accelerate to 11 kilometers a second just to escape the pull of Earth's gravity. Then, the ship that takes us to Mars will be assembled in space. But even with new powerful rockets and new spaceships, to cover millions of kilometers, new methods of propulsion will have to be used. When its engines are fired, a crew of 6 will be hurtled into the black of deep space.
Everyone ready?
Conquest of Mars is the ultimate engineering challenge. To get there now, will we resurrect radical technology from the past? Or will scientists have to push the laws of physics to their breaking point?
It's a very, very daunting engineering challenge, but that's what makes it exciting.
Engine start and liftoff of the Delta II rocket carrying the Spirit from Earth to planet Mars.
Spirit and Opportunity, those heroic little rovers, almost managed to make Mars look like an easy reach. Nothing could be further from the truth. Between them, the US and Russia have sent 38 probes and satellites to the Red Planet. 22 of those failed. Now, putting humans in the mix adds both complexity and danger.
Yeah, Mars is really a bit of a cursed target. And as a consequence, you begin to worry about what is the real chances of success first time round.
It would be like asking an ant to build a skyscraper. And ants are very good at building.
These people are going to be spending an awful lot of time out there without any hope of resupply, without any hope of rescue.
Rocket ships of all sizes and shapes have been designed, but most of them rely on...
In the 1950s, Werner von Braun and colleague Ernst Stullinger designed several manned missions for Mars. Von Braun would go on to help America get to the Moon, but he always saw Mars as the ultimate prize.
Our spaceship moves ponderously toward the firing site.
3, 2, 1.
In 1957, this is how the von Braun team thought we'd get to Mars. Hundreds of tons of parts and equipment would be transported into orbit above Earth. There, in the weightlessness of space, a flotilla of ships would be put together. It would take dozens of Earth launches to put all the components into orbit. A crew of 120 would pilot the 6 finished spacecraft to Mars.
The basic architecture of what he was suggesting 50 years ago is exactly what NASA is thinking about today in going to Mars.
Mars 1, all solutions look good to us.
But the big ideas of the von Braun era have been scaled down.
Roger, that's what we expect.
Scientists now think it can be done with fewer than 10 launches, with half the number of spaceships, and a crew of no more than 6.
We've broken things in space. We've lost brave women and men. So we don't want to go that way. We don't want to go at the hairy edge of survival.
But Von Braun was right about some things. As he predicted, the spacecraft that's going to Mars will be assembled in Earth's orbit from parts delivered by huge cargo launchers. The crew arrives only at the end of a short hop flight from Earth. They'll dock with the Mars transfer vehicle and then start the 6-month journey. Once they're in Mars orbit, the crew transfers to a lander which takes them to the surface, while their spacecraft stays in orbit above. When it's time to leave, the capsule blasts off to dock with the waiting mothership. 6 months later, back in Earth's orbit, the crew will transfer to a vehicle for the short trip home.
Whichever way you want to put it, going to Mars is going to require a lot of equipment working almost perfectly for anything up to 3 years. It will be a challenge.
Every journey begins with a first step. For Mars, it will be the blast furnace of flames lifting a heavy launch vehicle off the ground. But it will take much more than rocket power to get us there. Even at its closest, Mars is still 56 million kilometers away. What will take us there and back? At universities and space agencies around the world, big thinkers are wrestling with the question. There are dozens of competing theories and opinions about how to get to the red planet and back alive. But sometimes the best answers come from the most surprising sources.
It's a very, very daunting technical and engineering challenge, but that's what makes it exciting.
Canadian filmmaker James Cameron is on NASA's Advisory Council. Cameron's underwater explorations are legendary. And now, his fascination with Mars has inspired a radical design for a manned mission. Cameron looks at problems with a different eye than the scientists and engineers.
Colleagues like Jim Cameron are extremely creative because they thought about exotic, hostile environments, bring a new perspective to the idea of sending machines and people to places like Mars.
Cameron consulted with NASA specialists on every phase of the design, and all agree that job one for Mars is getting the huge mission, literally, off the ground.
The launch vehicle is the key to being able to go do a Mars mission because we need much more mass if we're going to go to Mars. So if nothing else, just the launch vehicles alone are the key thing that we're going to have in the near term that will enable us to go to Mars.
In the Apollo days, a single chemical rocket, the Saturn V, carried the entire mission, the crew capsule, the moon lander, and ascent vehicle all in one load. Mars requires bigger Earth launchers and more of them.
You've got to have a way of throwing big, heavy payloads up into orbit from Earth. Our biggest payloads go up with Space Shuttle, and they're 20 metric tons, something like that. You need something on the order of 80 to 100 metric ton capability to orbit.
The amount of stuff you need to go and come back to Mars is heavier than the International Space Station. We have yet to move anything that big, ever, in space. The analogy is going from a rowboat to an aircraft carrier.
To visualize the mass of the space station, picture 40 transit buses lashed together, floating in space. The approximate weight, 450 tons. To get that much material into space, NASA is developing 2 specialized launchers. Ares 1 carries the crew into orbit. The real workhorse is Ares 5. It's the space equivalent of an 18-wheeler, one that can generate an earth-shaking 9.6 million pounds of thrust at liftoff, enough to launch 175 Boeing 747s off the runway. Within minutes of liftoff, the Ares 5 accelerates to 11 kilometers a second when it breaks free of Earth's gravity.
It's the big commitment from the US in getting to Mars. If Ares doesn't work well, then we're just not going to Mars.
In the Cameron mission, the components for 3 Mars spacecraft, a crew vehicle, and 2 cargo containers would be carried from Earth to orbit on multiple launches. Once assembled in space, the unmanned cargo vehicles will be sent to Mars. The crew vehicle follows 2 years later.
The idea is to deploy as much mass out to Mars ahead of time as you can so that your humans can go out there really quickly. You don't want to take any more mass than you have to on that human transfer mission.
Faster means the crew spends less time exposed to the hazards of deep space. Mass is the crew's enemy.
In the case for Mars, a lot of that mass will be the fuel to get you there, the consumables to keep you alive.
James Cameron has a controversial plan to reduce mass. Cameron intends to take only enough fuel to fly one way. The fuel for the return trip will be manufactured on Mars. A bold idea. Too risky for most mission designers. It's never been tried before. But Cameron is convinced Mars has the raw materials to make it work.
But what do you know you have there? Well, plenty of carbon dioxide. Carbon dioxide has got oxygen in it, and it's got carbon in it. Well, carbon is the basis of your rocket fuel, and oxygen is the basis of the way you burn the carbon in the rocket fuel. Well, that's your ticket home. That's your fuel to come back.
Cameron is more cautious with other parts of the mission. Unlike other planners, he proposes that the landing vehicle travel with the crew. Sending it to Mars in advance is inviting trouble.
Eagle is undocked.
You're going to get into your landing craft, which no human being has touched for a couple of years now, because it's been sitting out there, freezing in orbit. And you're going to fire that puppy up, and then you're going to try to land on Mars. That strikes me as fraught with risk, as opposed to a spacecraft that you can keep online and healthy while you're transiting out there.
Cameron's lander concept is built around the rover, the vehicle for exploring the Martian surface. The rover will be critical for locating the Mars habitat and supplies already sitting out there on the surface.
The second you say that you're going to put stuff on Mars ahead of time, you have no choice but to land near that stuff. If you don't land near that stuff, you're not coming home. If you're 200 miles off course and you have no vehicle with you that can travel 200 miles over the surface of Mars, you're going to die.
There is no limit to the number of places where danger, deadly danger, could actually transpire.
In spite of the risks, space agencies around the world are taking on the challenge of designing the spaceships for a manned mission to Mars. The results are surprising. Russia's version of the vehicle that will take the crew on the first step of the journey has wings, while the U.S. goes back to a capsule design. Two radically different approaches as former enemies get set to rekindle an old rivalry. The Russians cherish their glory days in space exploration. Sputnik, the first satellite. Yuri Gagarin, the first human to orbit Earth. Past these gates where few Westerners have been is Energia, the aerospace company behind many of Russia's success stories. During the moon race, it built Soyuz, which still carries crew members from Earth to the International Space Station.
Soyuz has been an amazingly resilient vehicle. It's really worked on the philosophy, if it's not broken, don't fix it. That all said, you can't get beyond Earth orbit. And if the Russians want to be a serious player with the rest of the international space community in going beyond low Earth orbit, going to the moon, going to Mars, and they want to have a significant contribution, they've got to go beyond Soyuz.
Soyuz is now 4 decades old. It seats only 3 and cannot be reused. If Russia wants to take on Mars, it has to come up with a bigger, more versatile crew carrier for its cosmonauts. This is the future. The Russians call it Clipper, a 6-passenger space vehicle. Clipper will shuttle cosmonauts into orbit and dock with the spacecraft that takes them to Mars. For all its sophistication, Clipper relies on the same simple aviation principles that guided the Wright brothers.
Clipper has basic flight characteristics. It's just like a glider. Because it has wings, the landing will be similar to that of an ultralight.
His own flying experience convinced Clipper designer Sergei Stoico that wings are the surest way of bringing the spacecraft back safely. Clipper will pick up cosmonauts returning from Mars and then, like the U.S. Space Shuttle, glide home through Earth's atmosphere to a predetermined landing site.
Right now, Clipper is designed to carry crew members to and from orbit. But we are optimistic about adapting some of its technology to a spacecraft that will one day go to Mars.
Over the next few years, the look of this full-scale Clipper mock-up may change. Energia is hoping to lure investment from Europe to finance continuing development. The goal is to have it ready for a first mission in 2014. If all goes well, Clipper will get the big job of ferrying cosmonauts from Earth on the first stage of a trip to Mars.
We've taken the best elements from Soyuz and incorporated them in Clipper. Reliability and redundancy of key mission functions, which will allow Clipper to stay in flight despite minor equipment failures.
And that's not all. Energia is already training crews for the first Mars mission. A simulator prepares them for the delicate dance required to dock with the International Space Station. Those space station visits will serve as rehearsals for the day Clipper carries cosmonauts to a spacecraft headed for Mars. In the United States, NASA is taking a different road to the same destination. In August 2006, it unveiled its version of a new crew vehicle, one piece of a master plan to get to the Red Planet. This is America's answer to the Russian Clipper, the CEV, or Crew Exploration Vehicle, called Orion. Just like Clipper's role in the Russian program, Orion will be NASA's new link with the International Space Station. And one day, it will carry a crew to a vehicle headed for Mars. But NASA is also planning to road test its crew vehicle, taking astronauts back to the moon, an important training ground for sending humans to the Red Planet. NASA plans on landing astronauts on the lunar surface by 2020, then constructing a permanent base 5 years later.
In order to be able to go to Mars, we have to learn a lot of lessons on the moon, because while you can get to the moon and back in a few days, Mars will be several years.
Orion will be doing double duty. It will carry crews to the moon, and it will make a quick trip to Earth orbit to transfer astronauts to a Mars spacecraft. It's because of that dual role that Orion does not have wings.
When you want to go to places like the moon, when you come home, you're going significantly faster than when you come home from low Earth orbit. You can be going 25,000 plus miles an hour. And when you enter the atmosphere at those speeds, if you had a winged vehicle, it wouldn't stay winged very long.
We now can see a way to go forward to the moon and beyond to Mars. Without the CEV, without Ares, without putting those two elements together, we don't go out of Earth orbit. So in that regard, it's a very, very significant announcement that the United States has given us.
Orion borrowed the blunt teardrop look from the 60s era Apollo capsules, but it's more robust and a lot bigger. There's space for 6 passengers and 25 tons of supplies. Even better, it's built from a new aluminum lithium alloy, so Orion will be lighter than either Apollo or the space shuttle. But, like the earliest space missions, it'll return to Earth by parachute.
So going back to the future with the Crew Exploration Vehicle, the Crew Launch Vehicle series, is the right answer at the right time to get us back in the saddle.
With Clipper and Orion, the old space race rivals have devised new ways of getting their explorers into orbit. The first step in the big push to put humans on Mars. The next hurdle is much bigger. Design a propulsion system with enough power to drive a huge spacecraft to Mars and back. The lives of the crew will be riding on it. Just a few weeks into the journey, the crew will approach the point of no return. If a crew member was seriously ill or they detected a problem with the life support supplies waiting on Mars, now is the time to turn back to Earth. Past the point of no return, there is no turning back. Earth has already moved too far away. No rescue missions can be launched. They must continue millions of kilometers to Mars and circle the planet in order to come home. Engine failure is a death sentence. There's unanimous agreement that the easiest part of getting to Mars is building the launch vehicles to get the mission off the ground and into orbit. The real challenge is what comes next, designing a propulsion system powerful enough to drive the huge spacecraft from there to Mars across millions of kilometers of space.
The Mars exploration vehicle that goes from Earth to Mars, and most of it, of course, will come back, is going to be very, very large. We're talking about potentially hundreds of tons. We're talking about a vehicle that is probably comparable in size to the International Space Station, if you think about how big that object is, flying to Mars and back. To be able to push that vehicle successfully out of Earth orbit is going to require some pretty heavy-duty propulsion.
Some propulsion systems exist only in the minds or on the blackboards of physics professors. At the University of Washington, the electrical buzz coming out of this science building could one day shrink the travel time between Earth and Mars.
To go to Mars presently requires a 2.5-year return mission. Our concept is to go there and back in 90 days. Everyone ready?
Professor Robert Wingley's fast lane to Mars is powered by a laser-like beam of superheated charged particles. The particles of plasma cross the vacuum chamber in thousandths of a second. Wingley wants to generate a plasma beam powerful enough to propel a spacecraft to Mars.
You can beam the energy to your spacecraft and remove the need to carry large amounts of fuel, large power systems. It makes it cheaper, it makes it faster, and it's also a reusable system.
Okay, fire it.
It's futuristic physics that's narrowing the gap between science fiction and science fact. Here's how it works. A space station using its solar panels to generate plasma fires a beam at a passing spacecraft. The superheated beam propels the spacecraft to Mars without ever touching it. It's like the north poles of two magnets repelling each other.
It'll be going at very high speeds when it gets to Mars. Be going nearly 30 kilometers per second. That's again 4 times faster than a shuttle.
Stopping a ship traveling at that speed requires extraordinary precision. An unmanned satellite parked in Mars orbit must fire another plasma beam at the approaching space vehicle to slow it down.
We have, over the last year, made excellent progress in demonstrating it both experimentally and computationally, and we're totally confident that we can do it in the future.
It will be years before Wingley can perfect the plasma beam and get it into space. Mission designers who can't wait for this futuristic technology have 2 practical choices for propulsion through deep space. Chemical propulsion is created by mixing oxidizers and fuel. When the two react, flame and heat are squeezed through exhaust pipes and out the engine nozzle, creating thrust. A nuclear thermal rocket is a simpler, more efficient solution. Supercooled or cryogenic liquid hydrogen is heated by the nuclear core and comes out the engine nozzle as hydrogen gas.
Nuclear rocket technology is actually not particularly new. We were investigating the notion of using nuclear propulsion back in the 1960s.
We're on our way now to the Nevada test site where we proved that the nuclear thermal propulsion was the only way that we were going to be able to get men to Mars and return them back home safely.
Stan Gunn was one of a team of scientists and technicians commuting to the test site in the late 60s. Gunn developed the fuel mixtures. The tests were successful, but America's interest in space exploration was waning, and nuclear was a dirty word.
We had gotten to the point where we had proven out the capability of the nuclear rocket and were ready to go with a practical engineered system for a Mars mission, and yet nothing was done after that, and we got totally stopped.
But now, space exploration is back on NASA's agenda, and there's a strong case for nuclear propulsion as the best ticket to Mars.
It does offer some very significant advantage, primary among them the fact that there is a greater thrust that can be delivered by nuclear technology.
Another critical comparison. 2 equal-sized spacecraft, half a kilo of fuel apiece. The chemical rocket burns full throttle for 450 seconds. The nuclear fuel lasts twice as long. That means a nuclear-powered spacecraft is twice as efficient and can go the same distance on half the fuel. Jackass Flats, Nevada, sacred ground in the history of nuclear rockets. The stand where engines were anchored for testing, and the nearby hangar where rockets were torn down. Relics of the past that Stan Gunn believes still have a role in building propulsion systems for Mars. It's all still waiting here, like a museum exhibit. The diesel locomotive that hauled the rockets. Radiation counts here were so high that Geiger counters kicked wildly off the scale. All safety features survive, like the 6-foot-thick radiation-proof windows and the robotic arms that handled the rockets. And Gunn believes a few upgrades would make it safer and more acceptable to the public.
A problem with this rocket stand was when it was previously used, it exhausted its exhaust gases completely out into the atmosphere. However, with modern engineering approaches, we can have a complete containment system engineered to receive all of these gases.
The longest open-air test performed here took a nuclear engine to full power for just over an hour. Too brief, it seems, when you consider the 6-month journey time to Mars, but the numbers are misleading. The crew of a Mars transfer vehicle could need as little as 1 hour full throttle burn time to get there and back. Because space is a vacuum, no atmosphere means no friction to slow things down. Once it's built up ahead of speed, the spacecraft can literally coast to Mars. On the final approach, the spacecraft turns and the engines are fired to put the brakes on. Gunn says full throttle testing was done once, and it can be done again.
This test stand could be returned to operation for future NASA development of nuclear rocket engines. So the future is very golden.
One day, the Nevada desert may hear again the roar of nuclear rockets that pushes on, and there's now a detailed plan to harness nuclear power to get to Mars. NASA rocket scientist Stan Borowski carries the torch passed by Stan Gunn. Borowski believes the advantages of nuclear propulsion are just too good to ignore.
The benefits of nuclear are its higher gas mileage, which is twice that of the best chemical rockets. That means we need less propellant and fewer numbers of heavy lift launch vehicles.
Propellant is weight, and the less of that you have to haul into space, the fewer Earth launches you'll need.
So for a typical mission to Mars with nuclear propulsion, we need about 7 80-ton launch vehicles. With chemical, we need at least 11 missions.
That fuel efficiency will be critical to saving the crew if something goes wrong. Beyond the point of no return, they can't simply make a U-turn and head back. Earth is too far and moving away too fast. The only option, continue to Mars, circle the planet, and head back to Earth. With efficient nuclear thermal engines, they'll have more chance to get back home safely. During those long months aboard the spacecraft, the crew of a Borowski nuclear-powered vehicle will enjoy one comfort no manned mission has ever had before: artificial gravity. The crew will not be floating about on the way to Mars and back.
Our vehicles are long and linear and can be rotated like the propeller on an airplane to be able to generate artificial gravity for the crew, and this will prevent the debilitating effects on the body of prolonged exposure to zero gravity.
Wherever Borowski pitches the bold idea of harnessing nuclear propulsion for Mars, he faces some fearful people. Will his nuclear rocket become a nuclear bomb if somehow it blows up in Earth's atmosphere? The possibility of that happening is very remote. During launch to orbit, the nuclear engine is just cargo. It becomes radioactive only when fully assembled and firing. Out in deep space, any malfunction triggers an immediate shutdown.
Do we absolutely need nuclear propulsion to take people to Mars? Maybe not. But if we want to go for good, for a sustainable exploration story, the engineering solution that gives us nuclear propulsion, fission-based, nuclear electric, or nuclear thermal, will be a more efficient solution in the long run to opening up the solar system for people.
The propulsion choice is linked to another crucial decision: the trajectory or route to Mars. Not only is it at least 56 million kilometers away, it's a moving target. Plotting the right trajectory is life or death mathematics. Engineers and scientists are making thousands of important decisions about the spacecraft that will take us to Mars. But the planets dictate when the journey begins. Earth and Mars are millions of kilometers apart, moving around the sun at different speeds. Because their positions are always changing, the ideal moment to launch a manned mission to Mars only comes about once every 26 months.
It's unimaginably precise. It's probably the best analogy would be like threading a needle in the West Coast from the East Coast.
There are two ways of going to Mars. The choice depends on how long you want to stay on the planet. The long stay mission gives you about 1.5 years on Mars. On the outbound leg, the crew leaves Earth orbit when the two planets are relatively close. It's the same coming home, but the timing has to be perfect. Miss the window, and there won't be enough fuel to make it.
If the astronauts on Mars don't hit the launch into that window at just the right time, then they can't get back to Earth. They have to wait for the celestial mechanics to, quote, come back into alignment. You're talking about Earth and Mars being in the right places at the right time to allow the vehicle coming back safely to Earth.
The other option is a short stay on Mars, 30 to 60 days on and around the planet, and the route home is different. The flight path will take the ship past Venus, using its gravity like a slingshot to pick up speed for the trip home to Earth. But, as before, timing is everything.
There's no tide to carry you back to Earth. The planets move too quickly. We don't have rockets big enough. So you're stuck.
A few hundred meters from where the North Sea meets the Netherlands, the European Space Agency has been working on the critical decision concerning the two options for going to Mars. They've decided They'll learn more on the Martian surface in 500 days than a short stay.
We have a launch window for that every 25 months. To go to Mars takes 6 to 9 months. Then we'll be spending about 18 months on and around Mars, and it's going to take 9 months to come back, and that gives us all in all a 1,000-day mission, which is a very typical value for a Mars mission.
Italian aerospace engineer Loredana Bassoni oversees the team designing the spacecraft that can stand up to a 1,000-day return mission to Mars.
All right, so we're going to talk about the transfer habitation module, which is where our 6 astronauts are going to spend months and months of their time during the journey to Mars and back.
The Europeans are thinking big. The total length of the Mars spacecraft they envision is 100 meters, the size of a football field. Attached at the front of the transfer vehicle is the excursion module. It's a combination lander, temporary shelter, and ascent vehicle. The back half of the spacecraft is the multi-stage propulsion system that will carry the crew to and from Mars orbit. For the many months of the journey, this module will be the whole world to the 6 crew members.
We need to start talking about the requirements of this module. And Sylvia and Jean-François, can you start giving us some requirements about the transfer habitation module?
Okay, so for the volume requirements, this number comes up to be around 75 cubic meters per person, out of which 1/3 is for storage of consumables and equipment, and the other 2/3 are for the astronauts to live in.
It will be a tight squeeze. The total living space for 6 adults is 300 cubic meters, about the size of an average apartment. The rest of the space is packed with food, water, and equipment.
It's not just the nuts and bolts that's associated with the engineering. It's the humans interacting with that environment. You're talking about people who have to be a part of this colossal undertaking, and they've got to be comfortable with it.
Bassoni and her team are still learning the basics of manned space exploration. They've never launched their own manned mission, and they've yet to decide on a propulsion system. But no one wants to be left behind in the race for Mars.
ESA wanted to know how we could actually start planning European technology development based on what we would need when we go there. I hope ESA will go there, and I hope it goes there in my career time, but ESA won't go there alone.
Unlike the Europeans, Russian space engineers have years of manned spaceflight behind them. They've had great success with long-duration orbiters like Mir and the International Space Station. Now, they're applying the same technology to a vehicle that will carry cosmonauts on the next step of the journey to the Red Planet.
We can say with confidence that we have a prototype of a spacecraft for a manned flight to Mars.
Right now, that prototype sits under construction scaffolding. Energia's Leonid Gorshkov will convert this space station module into the new Mars ship that will carry up to 6 cosmonauts. It will be called MEK, the Mars Expeditionary Complex. Gorshkov is confident about his MEK module. It's proven technology, orbiting Earth right now. Zvezda is the service module for the International Space Station, housing propulsion, communications, and life support systems. MEK is reviving an old dream. Russia actually started planning for an assault on Mars more than 40 years ago.
Back in the 60s, when that project started, I was very young, and I had a junior role in its development.
Sergei Korolev, a star of Soviet rocketry, ran the top-secret project. Korolev is gone, but his accomplishments are honored. His technology is still studied.
The work on the Mars project under Korolev began on June 23, 1960.
Working under Korolev's direction, Vladimir Bugrov was a senior member of the design team. The designers went back to von Braun's Mars mission model of multiple Earth launches and orbital assembly. These calculations and drawings are all that's left from 4 years of work. 40 years before NASA even floated the idea of artificial gravity, the Russians knew it was necessary for Mars. Their crew vehicle would rotate on its axis, creating Earth-like gravity for the crew. Another design breakthrough was an onboard greenhouse for growing fresh vegetables. In 1964, the Kremlin shifted focus to the moon race, and plans for a Mars spacecraft disappeared. But the legacy of Korolev's technology lives on. It can be seen in Mir and the International Space Station, and now in a new Russian manned vehicle for Mars. Gorshkov is not reinventing, he's adapting. He's expanding this module to 6 meters in diameter and close to 30 meters in length. And the Russians have decided to play it safe, at least on their first manned trip to Mars. There will be no landing. The cosmonauts will stay safely in orbit above the red planet.
But from the engineering perspective, you've saved yourself a lot of work. The most technically demanding part, you could certainly argue, in any mission to Mars by humans is going from Mars orbit down to the ground and back again. If you elect not to incorporate that step, then you save yourself a lot of time, a lot of effort, and a lot of money.
Russia's caution with landing on Mars is well-founded. In 40 years of sending up unmanned Martian probes and satellites, Russia's record is 16 failures and only 2 successes.
You know, we've had very bad luck with Mars. With the Moon and Venus, everything went well. But it seems that Mars never wants to surrender.
The United States is also exercising caution. By returning to the Moon before attempting Mars, NASA will work out the kinks of a manned space exploration program that hasn't seen action in more than 30 years. No one wants to fail the first time out in a manned mission to Mars.
There's no forgiveness in space. You get it wrong, you kill people, brave explorers, and sometimes they don't give you a second chance.
The distance between Earth and Mars is slowly closing. People are dedicating their careers to the cause of a manned mission. From desert testing grounds in Nevada to a NASA rocket test bunker in Cleveland, Ohio, the right propulsion system will emerge. In Moscow, an aerospace giant will manage the huge cost of Mars by converting proven space station technology for the hundreds of millions of kilometers to the red planet. The engineering challenges of Mars are enormous. Will the technology hurdle best be cleared by nations joining together?
I don't think it's in the budget or even in the wishes of any nation to go alone. This is a big cooperation. This is for humanity to go there.
Sure, it would be nice to see Russians on Mars, but I'm strongly convinced that no matter who will develop the complex, the crew will be international.
Экипаж будет в любом случае многонациональный. We've had a go for auto sequence start. T-minus 10, 9, 8, 7, 6. We have main engine start. 4, 3, 2, 1, and liftoff.
Now we have a globalized world. Global economies, linkages in many new ways. I believe the way to go to Mars is to go together.
Mars 1, you are go for staging. Inboard cutoff. We confirm inboard cutoff.
You're going to see every single spacefaring nation of this planet contribute. You're going to see Chinese architecture there. You're going to see Japanese know-how. You're going to see Canadian activity. On board, principally a Russian-American vehicle, but nonetheless, Russia and the United States cannot get to Mars by themselves. It will have to be a joint undertaking.
Initiate auto-docking sequence.
When the multinational crew reaches low Earth orbit, they will get ready to dock with the spacecraft that will carry them to Mars.
12 был, одна сторона запись. Здрасте, аспачку за вас будет. Не понял. Аспачку за вас
5
будет.
meters. 4 meters. Looking good.
In the odyssey of Mars, the weakest link may be human. The breaking point of hardware can be measured. But what about the mental and physical limits of the crew? As the longest, most dangerous voyage of discovery gets underway, the human factor is the great unknown.